Welcome back to the highlights from the past 2025 Mini Symposia. I'm joined here by Roman Jakimczuk from Uppsala University, and you have been organizing a mini symposium on sustainable scientific computing.
Yes, correct.
Why do we need that? Isn't all computing sustainable?
Frankly, not all computing is sustainable because, for instance, let's start with hardware. If we run hardware for performance only and then we don't use this hardware, then we actually wasting energy. So recently, even in our small supercomputer in Uppsala, we started them changing frequency kind of on demand. So when resources are not used, we're not burning so much energy. And higher frequency means higher energy consumption. So it's like power time multiplied by time, and that's energy. And I started looking on this from the perspective of optimization, numerical optimization in terms of mixing precisions depending on the needs. And we do it carefully, so we don't have Ariane 5 issue, but we have some estimates and some error bounds, and that we do with the help of tools. And then we propagate this to computational fluid dynamics applications, and then we see that we can gain up to 2x energy and time saving. So that's super nice. So we approach it from algorithmic perspective. And now I'm looking a bit from what can we do from hardware. If we have memory-bound computation, so CPU is idle, then it means that we can lower frequency from the CPU and then still save even more from the hardware perspective. And we have gathered people from data centers that provided us insights from EPCC, how they manage heat, how they manage frequency. So they by themselves actually adapt frequency to slightly lower that top frequency, and then they have very nice benchmarks. This is what I learned. This was super new for me. And we had me that has a bridge between numerical derivation of algorithms and application that helps to adapt applications with the help of tools that scan these algorithms, these applications, and adapt algorithms with different precisions, and we implement and evaluate. And we had people from mathematics who provide error bounds, but modern error bounds using stochastic rounding so that they are much closer to reality. Because when we have exascale computing, problem grows, and then instead of having error estimate n, where problem size multiplied by mu, so it's like machine epsilon, we can have square root of n, and that reduces the error estimate by order of magnitude, and then we can have closer to reality error
So that's
estimate.
cool. So it's all kind of a co-design between, on the one hand, the application layer and the scientific problem, and the other, the operations of the computer. You're not necessarily changing the hardware itself, but you are changing how you're operating the hardware.
Precisely. Yeah. So we try to do this, we optimize on precision, and then we optimize in safe way, and as gain, we have time to solution saving, and we have energy to solution saving.
So how much can we save?
So we can save on CFD applications what we looked. It depends also how optimized is the code. If the code is highly optimized, we can save up to 30%. If the code is not so highly optimized, we can save up to 2x, because 2x is something natural. If we drop from double precision to single, then we reduce on memory bandwidth. And
but this is usage that can cost tens of millions of francs or euros per year, right?
Exactly.
So 50% is a lot here.
Yes,
yeah.
And we can actually fit more jobs on the cluster. We can more efficiently utilize clusters.
Cool. Is there any obvious next step? This sounds an important area.
Yes, so we have prepared last year a submission for Lawrence workshop in Leiden. We will be gathering this autumn about 50 researchers from hardware, programming models, algorithmic developments, and numerical analysis. And we try to define terminology, what energy means for each of us, what sustainability means. And we will try to have white paper and wider outreach to public.
That sounds like a great workshop to join.
Yeah.
Thank you so much for joining us.
Thank you, Eric.
Thank you.